Hello. Today we are going to look at the product and the quotient of complex numbers in polar form. So we've already looked at the product and the quotient, that is to say, multiplying and dividing complex numbers when we're dealing with them in rectangular form or a plus bi form. But there are some really useful things that happen when we write our numbers in polar form and try to multiply or divide them, because we can use the rules for trigonometric identities on page 15 in our log tables to really simplify the process. So initially it's going to look like a horrible mess, but it actually collapses into a very useful formula that develops into something called de Moivre's theorem, which is going to be the last thing that we focus on in complex numbers. So let's dive into it and see how our trigonometric identities allow us to simplify multiplying complex numbers in polar form. So I have my complex numbers written out here, Z1 and Z2. And in the log tables, when we get to de Moivre, we're going to write the modulus of our complex number as or, effectively for the radius out from the origin. As we know, that's what the modulus is. So just when we're using or, it still means the modulus of our complex number, as it always has. And other than that, we have theta for our angles, and that is what we need. So let's write this out. This is just going to be multiplying out and then looking at page 15 in our log tables to see what simplifications our trig identities can give us. So I write out my numbers. I have Z1 multiplied by Z2. And I'm going to write that out for you. So this is a horribly large looking bunch of brackets, but it is actually just two binomial type brackets with two numbers multiplied by them. So what we are going to be able to do is just multiply the OR1 by the OR2, because they're just numbers outside of our paired brackets, of our binomial brackets. So that's going to be OR1 times OR2. They're multiplied together. And then we have these two brackets multiplied by each other. And we're going to treat it exactly the same way as we would treat any algebraic brackets where we have two terms added together. So we're going to have the first thing in the first bracket by the second bracket, second thing in the first bracket by the second bracket. And I'm going to write that out for you. So I've written that out here. The first term in the first bracket multiplied by the second bracket plus the second term in the first bracket by the second bracket. And again, all of this is multiplied by my OR1 times OR2, the numbers that were sitting outside both of my brackets. So now I can multiply these brackets in. So cos multiplied by cos of theta 1 by cos of theta 2, cos of theta 1 by ai sine of theta 2. Even though this looks horrendous, it is applying rules for multiplying out brackets that we have known for years. So if we can keep a hold of the fact that this is actually fairly simple multiply, just with very odd looking terms, then we'll be fine. So I'm going to multiply that out for you now. So I have multiplied out my terms. I put in the little lines that you might have used early on in multiplying out your brackets, because again, this multiply looks weird, even though it's actually fairly straightforward in terms of the basic underlying algebra. So I end up with cos theta 1 by cos theta 2 plus I sine cos theta, I cos theta 1 sine theta 2, I sine theta 1 cos theta 2, and then I end up with I squared sine theta 1 sine theta 2. Now, I have consciously kept the theta 1s first and then the theta 2s second, because I know where this is going. It's going to page 15 in my log tables. So I want to keep one of my angles first all of the time, because that makes it easier to look at the formulas that I want. But now what I'm going to do is gather my real and imaginary terms. I know that I squared is equal to minus 1. So I'm going to be able to say that this is going to be minus this. So my two real terms are here. And my two imaginary terms are here. So I'm going to gather real with real and imaginary with imaginary. Now I've done that, I go to my log tables, page 15, and I look at my different identities and I say, do I recognize what this is and what this is? And I can see that from my log tables, this is cos of theta 1 plus theta 2. and this is sine of theta 1 plus theta 2. So I'm going to write that down now. So when I've done that substitution, what can I see? I can see that when I have my two complex numbers in polar form, when I multiply them together, I end up multiplying the moduli, multiplying the radiuses from the 0, 0, from the origin, and I end up adding the arguments. I end up adding the angles, theta 1 and theta 2. So when I'm multiplying, I end up multiplying the moduli, and I end up adding the arguments. And this is extraordinarily useful. Instead of having to multiply out big brackets, I am going to be able to, and it doesn't matter how many of these numbers I multiply together, I'm still going to be able to apply this rule where I'll just add up all of the angles and multiply all of the radii, which is very easy, and that's going to tell me what the product of my complex numbers is. Now let's deal with when we have the quotient, when we are dividing two complex numbers by each other. So if we have z1 divided by z2. So if I write this out, I have my two complex numbers written in polar form dividing each other, or the quotient of them. And what am I going to do? Well, if I have complex numbers that are fractions, one of the most common things I have to do is to make the denominator real. So I want to get rid of my complex stuff underneath here so that I have it so that I have the real and imaginary parts separated out. Very much the same as what we would have done when we had them in rectangular form, or a plus bi form. So that's what we're going to do. So how do we get rid of our complex denominator? We are going to multiply by the conjugate. So I'm going to multiply by the conjugate of z2. I'm going to write that out for you now. So this is my complex conjugate written in, and this is a reminder in simpler algebra of why it is that we are bothering to do that. I want to get rid of the I stuff underneath the line, and I see, as a reminder, what I'm effectively doing is just getting the difference of two squares. I'm multiplying a plus bi and a minus bi together, and when I do that, I end up with a squared plus b squared. So that is the aim of what we're doing underneath here, exactly the same as when we were getting rid of the complex part of the denominator when we were in a plus bi form. So I'm going to do this multiply out for you now. So I have now multiplied my OR1 and OR2 together, and my OR2 and OR2 together, and written that as OR2 squared. You can write it as OR2 by OR2 if you like. And obviously we're going to have a common factor there and divide it out in a second. But for the rest of it, for multiplying out the bracket, the first thing in the first bracket by the second bracket, I have done that here. And then the second thing in the first bracket by the second bracket. And I have done that top and bottom. And now I'm going to multiply this out just like we did up here. Now, having multiplied all of this out, I am now going to gather real with real and imaginary with imaginary, knowing that I squared is going to be equal to minus 1. So I'm going to have minus by minus is plus. So this is going to be plus, and this is going to be plus, and it's going to be real. And on the bottom line, I can see that I have two like terms. I know what's going to happen here. My imaginary terms are going to sum to 0. Because this is why I did the multiply in the first place. This is going to be minus this and plus this sums to 0. I can see they're identical. And here I also have the same angle. So I have cos theta 2 by cos theta 2. Well, how would I write that shorter? I'd say cos theta 2 squared. And likewise here I have sine theta 2 and sine theta 2. That's something by itself is squared, so that's going to be sine theta 2 squared. So I'm going to have cos theta 2 squared plus sine theta 2 squared on the bottom line. And we maybe know an identity that's going to help us with that. And I can also divide out my OR2 and OR2, that's a common factor, top and bottom here. Now, having taken out my common factor of my OR2, top and bottom, I have now gathered my real and my imaginary on the top, and I have gathered my cos 2 theta squared, sine 2 theta squared on the bottom line. And I know that cos squared plus sine squared of any angle is just going to be equal to 1. This is one of my key identities that I know in trigonometry. So this part is just going to equal 1. All of it is just going to equal 1. And then on the top line, I can go to my trig identities and see what these work out to. And I'm going to find that the real part works out to cos of theta 1 minus theta 2, and the imaginary part is going to be sine of theta 1 minus sine of theta 1 minus theta 2. And I'm going to write that out for you now. So when we do that substitution, I have now written this in a little bit of a way anticipating where we're going to go with this in terms of de Moivre's theorem, but we end up just dividing the radii, which is just dividing the modulus, or moduli, and we end up, by our trig identities, we end up seeing that we subtract our angles. And again, we can see how useful this would be if we had a bunch of complex numbers to multiply together. Instead of having to multiply out a whole pile of brackets, we're able to throw them into polar form, and then we were able to just subtract our angles and divide our moduli. So I've written that in as a little note at the end here, just like we did for the multiplying part, if you want a consolidation of what we've talked about. So these derivations link in very well between trigonometry and complex numbers, and therefore they could be theoretically looked at in an exam type setting, because they are linked between both